So, welcome everybody. The official language will be English so that everyone can understand. Today we are trying to understand a little bit about the home and building automation system. The idea is to give a general overview with some focus on three technologies we are using in the dog gateway. So the idea is to start to grasp what are the complexities and what are the low-level issues we are tackling when developing something with dog or inside dog. And on the other side, we want to provide some hint, some information about how to abstract, how to deal with the specific idiosyncrasies of the technologies so that we can bridge those technologies to a unique abstract representation, which is the one we use in dog and we expose to external applications. So the talk is organized in three main parts. One very short, which is for defining the context basically. So what is home automation, what is building automation, what are the differences, what are the technologies involved in both. And then we focus directly on the three technologies. I thought before they are the Open Web Nets system from BTC Nolegrand, the KNX system, which is the European standard for home automation, let's say, and the Modbus system, which is a relevant counterpart in the industrial setting side. We dive in the three technologies down to the protocol level so that we can understand what are the real complexities, what are the differences, both in the representation of data and the messages and in the different assumption laying at the basis of the interaction between devices. We will see that they are quite different one from the other. And afterward we had a little conclusion on designing and modeling those technologies and other technologies for integration with dog. The idea is not to understand how to modify the technology because we don't want to touch it. The idea is to understand how to conciliate the technology particular features to the dog representation. Okay. So there are some choices to take. Some are soft, some are hard, but we need to take them if we want to interface those technologies. Okay, so starting from definition. I try to put here some really dense definition of home automation and home automation system, domotics and so on. I don't want you to read everything. What I want to highlight here are the keywords. So what are the principal features, the main features that characterize and define a home automation system. And the idea is that I try to highlight in bold the relevant keyword, but the projector is not so good. Anyway, I can read them. So the key features are, on the left side, to control basic home functions and features automatically and sometimes remotely. On the right side, there is an home automation system is an integrated automation system specific to the requirements of a private residence. So on one side we automate some home function and we make them accessible either locally on the remote side. On the other side we are saying that this technology is specific for the home. And that's the main feature of home automation versus the building automation that we will see is a little bit more general. And the definition on the bottom, which comes from the free dictionary, so this is a general dictionary definition. Interesting is based on the word domotics. That means that stems from domus and informatics. And the broad definition is information technology in the home, and this is very broad because it can include everything from PC-based interfaces to home automation and other things. And then they specify a little bit more the definition, saying remote lighting and appliance control, plus everything that makes the home digital. So also entertainment, multimedia, and interaction, basically. So summarizing, we can distinguish home automation from home automation systems first, and we can agree on the definition of automation, saying that is everything that has to deal with the automation of the home, of the private home, of the residential home. And basically, it is designed for providing control, possibly remote, of lighting, heating, ventilation and conditioning, appliances, plus other systems. So PCs, screens, and so on. And this is home automation. A non-automation system is a system which provides some automation. And it is basically based on a computer, which can either be a general purpose computer, but usually it's a kind of embedded computer, something very small that can be mounted into a wall rack or something like that. And the main task of a home automation system is on one side to provide home automation, on the other side to coordinate and integrate the devices which participate in the home automation plans. So possibly we have to face some communication issues, like different communication networks, different protocols. We already know, since almost all of us have a slight knowledge of DOG. So we need to bridge technologies in general. Although in a home, especially if the home is built from scratch, usually there is just one main home automation technology. We still need to bridge technologies because we may have other devices inside, like a smart fridge, a smart dishwasher, which uses a different technology with respect to the main plant. Okay. So even if it seems that bridging technologies is not so important in the residential side, actually it might be. Okay. On the other side of the medallion, we have the building automation system. And we want to understand what's the difference with respect to the home automation system. Since when we started to work on DOG, we started from home automation system, then we are evolving to building automation system. But what are the differences? And can we evolve freely from the home automation to the building automation? And the idea is that if we look at the keywords, they are almost the same. Because a building automation system, for example, on the left says it's a comprehensive and coordinated control of one or more major system function required in a facility. So control and automation, exactly like in home automation. And the functions are heating, ventilating, and air conditioning, the same, lighting, plus some other function like fire, like safety, like transportation, and so on. So it seems that a building automation system is just a kind of superset of home automation. And if we look also at the free dictionary definition, which is much shorter than the one for home automation, it says a fully integrated control system in which building services are monitored and controlled by a computer-based system. So, in turn, another time, control through a computer. So if we try to define in the same way of home automation, the building automation, we get a really intersection between the two. Because we can separate building automation from a building automation system, like in the home case, and the functions are very similar. In particular, the building automation refers to more functions with respect to the home automation, because it refers to security and access control. In the home, usually we don't have to care about access control, or not so much. Fire detection alarms, heating and ventilating, air conditioning, lighting, air quality, which we take care of in a building, but not in the home. Smoke detection, intrusion detection, environmental control, and so on. So many more aspects of the same problem, automating a building in general, which might be a residential building or bigger building like an office building or an industrial building. And a system, a building automation system, is just another computerized system which provides building automation. So they are structured in the same way. They tackle the same, almost the same things, just one is broader than the other. So if we want to compare them, I would say they are almost one a subset of the other. I said almost, but not completely, because there are certain functions in home automation which are not needed in building automation, or which are not in the focus of a building automation system. And that's why I just designed them, drawn them like two intersecting ellipses, but not completely overlapping ellipses. So our hypothesis of working with the same approach to building and to home automation is supported by the reality, because actually they are overlapping. Okay, so we can try to, at least try, to devise a single approach for both. And the idea is to understand how, what are the differences between these technologies and what we need to do for tackling them. Okay, and here comes the hard side. Because okay, the needs are the same, we expect just few technologies for addressing them, but this is the reality. So many technologies, each one stemming from very different approaches, and mixing and messing up inside the domains of home and building automation. So basically we have some computer-derived standards. I'm speaking of Wi-Fi, for example, which just provides connectivity inside the environments, or Bluetooth, another connectivity provider. We have something which is in between computer-based networks and automation, like ZigBee, UPnP, DLNA. ZigBee, it's a kind of network transport plus some specification for the automation. UPnP, DLNA have nothing to do with the automation, but they have very much to do with entertainment and multimedia content sharing. And since this is one of the aspects of home automation, they are also inside the cloud of protocols and standards to consider. And I put them in the home automation side, as you see. And then there are many different automation standards. Some of them are really old, like RS-485, which is a standard, serial standard for transferring data between metering devices, basically. Some of them are new, like INOCEL, which is a wireless standard for communicating for devices designed mainly for providing home automation or building automation in those environments where wires cannot be installed. So they are communicating wirelessly, and they have the particular feature that this protocol is completely open. Okay, so everyone can download the protocol specification and try to implement the device. And then there are many other standards. Some of them are industrial. So if you think of CAN, MBus, Modbus, they are coming from the industry. CAN is widely used for real-time automation inside the industry. So for example, almost all vehicles have inside the CAN network managing the different subsystems. MBus is a bus specifically designed for providing metering information. Modbus is a kind of bridge allowing to transfer data between different subsystems and also to provide some automation capability. Basically, it stems from the older PLC programming in the industry, and it's the de facto standard in the industry, one of the de facto standards. Echelon and LoanWorks are mainly designed for metering and for controlling devices in the industrial setting, and in particular the Echelon one is the one used by the electric facility in Italy and in other countries to control the electrical meters installed at every building, at every home. So they have a management network using echelon technologies. KNX here is involved because it is in between building and home automation. It can do both. Actually, it is a little bit more towards building automation because it starts to be a little complex. And it is bigger than the others because it aims to be the European standard for building and home automation. And I'm saying it aims to be because the consortium is there. They are quite active, but actually they are still, let's say, fighting for gaining this uniformity around Europe. And also this is a closed consortium, so you need to pay a fee for being part of the KNX community. On the other side, there are some home-specific protocols and technologies which share the same, let's say, objectives, but they tackle the problem in a different way so that less skills are required for installing system, basically. So the My Open system, for example, is coming from formerly from BTC, now from Legrand, and only requires electricians to install the elements because the configuration, as we will see, is based on some kind of electrical connectivity, electrical connectors put on the back of devices. So you just have to switch some connection beside the device and everything is configured. On the other side, if you want to configure a Modbus system or a Connect system, you need a PC and a configuration program. So that's the main difference between the approaches and many others. So if we want to talk with them and to integrate them, we are really scared. Many different things, many different approaches. Almost all of them are independent and different. Almost all of them try to say, okay, we are compatible with the others, but the compatibility is given in the sense that the main technology is the master, the other technologies are the slaves, and the communication is just one way. Okay, so if I have my open system, I can control a Connect system, but this is not a peer-to-peer integration. This is an inclusion of the Connect system inside the My Open system. So the My Open is controlling the Connect system. They are not at the same level. Okay, so this is the main scenario. Every time that we need to integrate technologies, and we want to do that using native technology on one side, the interaction is like a kind of master-slave interaction. Okay. So let's try to put a little bit of order inside those technologies, because they are many, they are really difficult to organize and really difficult to tackle. So I try to put a kind of organization based either on the technology or on the application. So let's try first on the technology, on the network technology in this case. So I divided the main network technologies which these standards are using, and they are basically bus technologies, power line technologies, and wireless. Bus technologies are based on a bus, so on a kind of wire cabled inside the home or inside the building, and they have the advantage that they can realize all the functions by just using one wire instead of many wires. On the other side, power line solutions exploit the already existing power line connection inside the building, and they basically encode information by transmitting high frequency signals on the main power signal flowing on the connectors. And the wireless systems are using wireless transmission, sorry. They have different frequencies and different modulations, and they usually are based on a mesh network topology. So they are composed by nodes which interact with each other with no specific relations. The relations are established at runtime, so that even if a node in the network fails, the communication can reach all the other working nodes. Okay, this is really a really broad definition. And I try to separate the technologies that we saw before according to the network technology. So we have my open KNX Modbus Echelon DALI, which is for lighting automation, CAN and MBus are based on bus technology. Some of them are starting to bridge toward other technologies. For example, KNX and MyOpen are slightly moving towards wireless also. On the power line side, we have Echelon, and that's why the electric facility in Italy is using Echelon for accessing the meters, because it's power line. They harm the power lines distribution, so it's a reasonable choice. X10, which comes from basically from UK and US, is not a really common standard here in the continental Europe, and Eastern, which is another standard coming from the US. There's nothing to say much about power line. It is pretty similar to the bus solution, but with the advantage that you can just exploit the already existing connection. So you don't need to wire other cables inside the home. And in that case, it's more useful for retrofitting existing installation, because you don't have to rewire the plant, you have just to plug the new devices. And on the wireless side, there are the three technologies which we were mentioning before, that are ZigBee, Z-Wave, and Inosian. ZigBee, it's a standard, it's free, almost free to access, but the problem is that it is basically designed for being a network transport layer. There are kinds of specification for home automation for smart devices, but every producer, every vendor is implementing its own variation of the specification. So while the network is standard, what's above the network is really not standard. The Z-Wave approach is completely different. It's a closed protocol. You need to pay for having all the information about the protocol, but it's widely diffused. So you can find many Z-Wave devices. They are quite cheap. They range around 100 euros, no more, for the most complex devices. And they interoperate between different vendors. So if you buy, I don't know, a plug, an automated plug from Dewey, which is one of the producers of Z-Wave devices, and you buy a button from Evergreen, which is another vendor, then they interoperate without any problem, because they both stick to the Z-Wave protocol, which is really strict. Okay. Inosian tries to do what the Z-Wave does using a proprietary protocol. Inosian is trying to do the same using an open protocol. But the problem here is that the technology is quite new, and the protocol is there, but there are still few devices using the Inosian protocol. Okay, so even if it seems to be more promising in the long term with respect to Z-Wave, it has still to spread around the world. And these are also useful for retrofitting, basically, because you can dispose of the device all over the building or the home without almost any constraint apart from walls. So if you have walls between devices, then the communication range shortens, basically. So if you have 100 meters of communication, of maximum communication distance in the outdoor, inside, that dramatically drops to 10 meters or 7 meters or 15 meters. It depends on the thickness of the wall, on how much metal is inside the wall, and so on. And the other problem for wireless technologies is that some of the devices of the technology are battery powered. So they require battery substitution at fixed intervals. They usually last for at least 6 months to 1 year, so it's a reasonable time for substitution, but they need to be substituted. So if you have a big building with hundreds of devices, then you need to pay someone just for changing batteries. And that's why usually in building automation they are not so used. Okay. Oops, sorry. Okay. Other division is by application area. This is much faster. So if you try to divide technologies on the basis of the application area, we have some main application areas like automation, pure automation, that might be building, home, or industrial automation, lighting, metering, entertainment, and general purpose. General purpose is really simple. They are just network technologies, so Bluetooth and Wi-Fi are inside this last set. Entertainment also is easy, DLN, UPnP, and whatever protocols are used for sharing multimedia information, but we don't care very much about them because they are not much about automation, they are just about sharing of content. On the left side, there are more important application area, and they show different presence of the different technologies. For example, if you look at the KNX technology, is almost in all application areas, while there are other technologies like MBUS which are just in some of them. So for example, KN is designed for real-time control, so you find it in control system in industrial settings like in machines or inside vehicles, but the application is really restricted to real-time control, while other technologies are more general, and so if you get KNX, MyHome, Instion, Echelon, and so on, they are almost applied in all the application area. For the lighting, there is this daily standard, which is the de facto standard in industrial buildings for lighting automation. So if you are going to install something in a big building, then you will likely encounter some daily automation system there. So this is just for making us aware that if we are going to build the automation, we need some way to bridge to daily. This can be done in different ways, directly or by using another technology, of course. And on the metering side, the same protocols. If you look here, there is KNX like in the automation or lighting, plus these two which are older and pretty much diffused in existing buildings, and they are the RS485 and the MBUS. And these are for professional metering usually. So for example, here at the Politecnico there are a couple of meters using RS485, and then they are bridged to Modbus. If you go in industrial setting, you find very often MBUS devices connected together. So if you want to get information from those meters, you need to bridge to those technologies. So many technologies with different purposes, with different communication networks, and this is our panorama. We need to work with them. We need to integrate them. We need to find a way for conciliating the different approaches together if we want to provide a uniform access. And that's the basic assumption lying at the basis of the dog design. We want to bridge everything. We want to abstract everything. Okay, it's a little bit ambitious, of course. Okay, so what are the challenges? What we need to take into account for doing that? First, integration. If we are in a building, a big building, we will encounter many technologies, and they need to speak to each other if we want to have an efficient building automation inside the building. So they have different electrical requirements, they interact differently, they communicate differently, probably they have different communication means like bus, like wireless technology and so on. And they have a different temporal behavior, or they expose different information, so we need to find a way for integrating and interoperating these informations all together. Some of the problematics related to integration are also related to interoperation. What's the difference? Basically, if we want to integrate, we get all the information from all the networks. If we want to interoperate, we want to operate one network from the other. So we want to act as a bridge rather than as a collector. Okay? And in that case, we need to also consider the interaction modality. So if I press a button in a Connect system and I want to switch light in an Ocean system, I need to do the proper conversions, not only between protocols, but also between interaction modalities. For example, might be in Modbus, we have a master-slave approach. So commanding means writing a value in a register, while in Connex, commanding means sending a data point on a given address. This is different. We need to bridge these different operations. Okay, so more complexity with respect to just integration. And the really hard problem is this one, modeling. If we want to provide uniform access, we need to find a way for representing all these technologies, all the capabilities of the technologies in a comprehensive way and in a uniform way. So we need to find a uniform representation that can apply to all technologies. Maybe not by overlapping the 100% of the functionalities provided by the technology, but at least can apply to all of them. So for example, our vision started from the idea that the lamp is a lamp, whatever is the technology used for controlling the lamp. Okay. So if we want to control a lamp, we just want to switch it on or off. It doesn't matter which is the technology we use. Okay. So starting from this assumption, we need to find a way for representing all the different network level issues. Okay. So this is our goal and our hard task to carry. Okay, so having in mind what's the goal, let's try to analyze a little bit in deep the technologies with some particular focus on the assumption, on the network topologies, and on the idiosyncrasies that we need to take into account for bridging and integrating them. Okay, so if you have any question, just stop me, because from now we are going very deep in the technology. Not extensively, so after this we are not able to directly speak every protocol, but at least we can understand what are the differences. Okay, so let's start from the simplest one, which is the MyOpen Open WebNet system. It was developed by BTCino in the origins, and now it has become a Legrand standard because BTCino has been bought by Legrand. It was born as a proprietary bus, which was named SCS. Okay, it actually uses a proprietary protocol on the bus. Okay, so it is still closed in some way, but it has some open access facility, and we will see which are. The main feature of MyOpen is that it's really easy to configure. If you look at this picture, you can see here, this is a device, a MyOpen device. This is a clip, and there are some electrical bridges. You take the bridge, you put it in the correct place, and the device is configured. So you can change the entire automation plan by just switching bridges on the back of devices. And this is really suited for electricians, because they do not have anything, they do not need to know anything about computers, about programming. They have just to bridge electrical connection, and they are used to. So this is the main advantage of this system, and that's why it is mainly designed for home automation, because inside the home you just call usually the general electrician, not a specialized one, not one with particular skills. So that's why they use this. And the big design choice that they made some year ago is to keep the bus closed, but to open the protocol to access the bus. So even if the communication on the bus is closed, so we don't know anything on the low-level communication on the wire, what we know is the protocol to speak with the gateways from this technology, so we can interact with the devices on the bus. And this protocol is called Open WebNet. That's why I was using both names in the slide: MyOpen and Open WebNet. OpenWebNet is the name of the protocol, and as the name says, it's open, so you can download the specification from the OpenWebNet site. And it is designed to offer access to the network capabilities from almost all the devices able to open a connection. So it originally was designed for providing web remote access to the bus, and then it was opened for all the other applications. And it reflects this origin by using a protocol which is designed to work on a phone line. So it's really minimal. It uses DTMF tones, so just the numbers plus the sharp and the asterisk, codified like sounds. Okay, and that's why this protocol is a kind of protocol which is pretty distant from a computer-based protocol. Okay, it's much more like the protocol we use for opening doors, for example. If someone is ringing me from the door, I just hit *1 * for opening the door. And this is exactly the kind of communication used by the OpenWebNet protocol. So, for example, that line here, which is a command in the OpenWebNet protocol, means switch on the lamp with the 12 address on the bus. The first one means lighting, the second means on, and the 12 means is the address of the device. So by sending this to the OpenWebNet gateway, you switch on the light. Okay. Okay, this is really distant from what we said before. A lamp is just something that can be switched on or off, because we need to bridge this information. So let's try to dive a little bit deeper in the protocol. This protocol is based on two different types of communication. You can open two different sessions, basically, for speaking with the gateway. One is called the command session, and as the name says, is for sending commands, different kinds of commands. And the other is for monitoring what's happening on the network, and it is called the event session. So the idea is that the command session is a kind of application-initiated communication. So from the application side, you send commands, you ask for device states, you ask for measures, but the application is the first actor in the communication. On the other side, on the event session, we work in an event-based interaction. So usually the bus is the initiator. Something that happens on the bus triggers an event generation in the same form almost, and then the application is responsible to possibly react to the application. Okay. So that's the difference. And if we want to interoperate or integrate this technology, we need to open both connections, basically, because we need to listen what's happening on the network, because perhaps we want to bridge the network towards another, so we want to listen that a button has been pressed, because we want to route the command to a connex network. But on the other side, we need also to command the devices on the network. So from the requirements side, this technology requires to have two sessions open at the same time, if we want to interoperate and integrate. Okay, if we try to go a little bit farther inside the protocol definition, we can say that the protocol is based on tags. Tags are just numbers plus the sharp sign, which are separated one from the other using an asterisk sign. And the end limiter is provided by two sharp signs without any characters between them. So really simple. Really hard to bridge to very high level representation, because we need to bridge numbers and symbols to something like switch the lamp on. And the other difficulty that we have, and we are seeing why, is that even if we can require commands, we can send commands, require measures, we can get states, we get the same format for requests and for events. So what's the difference? The difference is the session, but we need to take into account from which session the message is arriving. So, other complication. Okay. So, let's dive a little bit inside. Usually a command in MyOpen is structured along 3 main tags. The first is named who, the second what, and the third where. Who identifies the functionality, the class of functionalities. They define a set of functionalities, basically they are 17, and each set of functionality has a different what table. So the what field depends on the who value. Okay, so the number in the what position changes depending on the who position. So for example, if we are in the lighting case, the who will be 1 and on will be 1. But if we are in the multimedia case, on will be 0. Okay, so another problem. The same command is different depending on the who tag. Okay, and we have all those tables because they are open, so we need to convert our information to the protocol information. So in the standard there is this who table, and for each who there are the what tables that allow us to understand what can we do with the system. And these 1 to 1000 numbers are the numbers reported on the electrical bridge that we put on the back of the device. Okay, so we can tell this is a lightning component by putting a 1 tag on the back of the device. Additionally, there is the where tag, which is the locator for the devices. So by using the where tag, we identify the address of the device on the network. This is a 0 to 255 identifier, so we have a maximum of 255 devices per each who, basically. And this where, together with the what parameter, can have more parameters, because perhaps a device is representing more information. If I have a multimeter, the same meter, so the same where, is providing multiple information, 1 per phase, for example. So we need additional parameters to identify which measure we want. And that's why the what and the where tags can have parameters to better specify what we are expecting the devices to do. Okay, so really deep. Let's say some example. The first one is the one that we already saw. It's switch on the lamp with address 12. So who is 1, lighting, on is 1, and the address of the lamp is 12. If the lamp is the lamp in the kitchen and we want to represent the lamp as the lamp in the kitchen, we need to translate lamp in the kitchen to 12, translate on to 1, plus translate lamp to the 1 who. Okay. If we want to switch on the webcam, everything is different, because the address is the same, so we need just to match webcam with 4000, for example, but the command is different, it's 0 instead of 1, and the who is different, it's 7. If we want to switch off the temperature control, this is different, because for example off is 303, okay, completely different. And 1 in that case means zone 1, because the temperature is working by zones, not by addresses. So a slight variation on the message composition. Plus we have scenarios commands like this, that means switch off all the lights. 1 is lighting, 0 is off, 0 is the network address. So everything on the lighting. Okay, really complex with respect to a general representation, at least. Okay, so we nearly ended with this first protocol. What are the problems and the idiosyncrasies that we need to take into account when we are designing something for integration with dog, basically? So this network has an explicit state notion, so we are able to understand in which state every device is, okay? But we have some problems. For example, we have the same format for state changes and commands. So if we are listening on the network, what's the difference between a state change coming from the network or a command sent by another application? There's no difference. They have the same format. State changes are delivered on only event session, only monitoring sessions. So if we don't open a monitoring session, we are not able to detect state changes. And they are delivered only for active device. I use the word active in quotes because this is only for meaning all the devices that actually perform some action, like an actuator, like a light switch, but buttons are not active because they are pressed by the user, but they just send commands on the network. And their states cannot be detected, even using an event session. So if we want to know that a button is pressed, we cannot. We can infer that the button is pressed by listening to the state change of the actuator connected to the button. Okay. Okay, and this is the second part. This is these are the idiosyncrasies of the protocol. They are few, but challenging in a sense. Something to take into account when we want to bridge our abstract representation to the low level. Okay, and we are at the end we are trying to establish the connection between the abstract representation and the low level technology. Okay, any question about this technology? Okay, no question. I suppose that everything is clear for the moment, or maybe it's too complex. In that case, we are going in a more complex domain, which is the one of KNX. Okay. So KNX is much more complex than MyOpen. It has a network approach. So everything is more similar to a computer network than with respect to MyOM. Okay. So it is more informed about the OSI layer specification and so on. And it comes basically from a merger of different technologies. Okay, so there were some earlier home automation technology, building automation technology in Europe, which were the EEB, EHS, and Batibus, and they joined together from a first consortium, which now is expanding, including many other vendors. And they created the KNX standard as a merger of these automation protocols, trying to extract the best features, but of course carrying also some of the shortcomings. The approach here is completely different from the MyOpen. While in MyOpen the device is a dumb device in a sense. We just configure the device by bridging electrical connection. Here the device is intelligent. It has a kind of computational power on it and some small programs running on the device. So every device is a small computer, let's say, running a program. And this program can be changed. And this is one of the most difficult things when we work to KNX, because the device can come without any program and we can download on the device some different program depending on the needs. But if you do that, you are encountering problems, for example, with versions. One version is not compatible with the other. With memory, maybe the new program is too big for the memory on the old device, and so on. Okay? So they are adding additional complexity to the programming side. And reflecting this additional complexity, we have two modes for configuring the device. One, which is the most used in the building automation side, is called the S mode or system mode, and requires a computer with a specific program, which is named ETS. Okay? Everything is done with this program. So with this program, we download the application on the components, we bind the components together, and we build an application that spans over multiple devices. So if I want to build a lighting application, I will be coordinating the programs on different devices. For example, the program on the light switch, the program on the light sensor, and so on. The other mode which is available is something that tries to mimic the simple approach of MyOpen, or at least something that can be used in alternative. And the idea is to configure the device without manipulating the network using a PC. So we just operate on the device and we configure it. It is something in between the electrical bridge-based configuration of MyOpen and the button configuration of Z-Wave devices and the other. The idea is that you have some kind of human interface on the device which allows you to configure it. But this is rather new, and there are a few devices supporting. And it's complex. Even more complex than programming using ATS, especially if you are used to using ATS. So almost all KNX installers are using ETS, and they almost completely ignore the E mode. And this is reflected by the fact that the devices supporting the E mode are much fewer than the ones supporting S mode. Okay. In Connex, we have a general architecture that we don't have in MyOpen, okay? And this reflects the more informed approach to the network. We have some main layer, a main communication layer which exploits different network communication technologies. So, for example, TP1 is based on twisted pair, PL on power line, RF on RF transmission, and there is also some communication over Ethernet. There is a standard addressing schema, so all the devices independently from the communication network are addressed in the same way. Basically, there are two kinds of addresses. One is the individual address for the device, the other is a group address, which is used for binding devices together. On top of this communication layer, we have the protocol, which is standard, uses standard objects, and it is defined in the 2 or 3 books. Okay, you can get access to those books by paying a fee for joining the KNX consortium. So, for example, we are part of the KNX consortium by being an academic partner, so that we have all the books on the protocol and on the architecture. This group of communication technology, addressing and communication, is called kernel, so it's the lowest layer of the architecture. Then there is a common runtime that basically permits to connect the devices together and to make the devices interact with each other. And this is usually done by binding what are called data points on the devices. We are specifying better in a few slides. And on top of this common runtime, there are the 2 operating modes, which are the S mode and the E mode. Okay? So this is a kind of 3-layered approach to the network. A little bit more complex than MyOpen. Okay. Let's understand how the communication between devices work. The idea of KNX is to build a distributed application. So here we are not speaking of switching on lamps or controlling shutters, opening doors. We are speaking of applications that might include also switching on lamp or closing the doors, but in general they are designed for doing some general task altogether. For example, safety or fire detection. And this is the application, and then all devices participate to the application. And this participation is based on the concept of data points. Every device, every physical device has a software on it running, which exposes a set of data points. Data points can either be inputs, so something that the device expects from the external. Outputs, something that can be sent by the device. Some parameters for changing the device behavior. Some diagnostic data on the device. So we have this data point, and we program the application by connecting the data point together. And these data points are not arbitrary, so the vendors are not allowed to invent new data point at every time, but they are standardized. So they are defined by the standard, and every device can only expose a subset of data points depending on the kind of device. So if you have a meter, basically all the meter will have almost the same data points. What changes is if the meter is just a single meter or a multiple meter. In that case, there will be more or less data points, but the types are the same. So if you are expecting a current data point, then the current data point is present in a ABB meter or in a Schneider meter or in another meter, because they standardize these data point types. Okay. So how can device communicate? Basically, they read and write the data points. Okay. So one device reads a data point from the other and takes some action, or writes a data point on another device requiring some action. So for example, if I want to switch on the lamp, I will write the switch data point on the lamp actuator, and I will put, for example, a 1 value inside that data point. That means that the actuator software reads 1 and switches the real relay to which the lamp is attached. And so the application semantics is basically based on the format of data exchanged between data points and the binding, how we can connect the data point together. And also here there are 3 binding schemes, so the protocol is really complex. One is free, which is the one that we are using typically in our cases in the lab, in the installation we do outside. Then there is a structured binding, which is similar to the free binding plus some constraint. And then there is a tagged binding, which is designed for working in the E mode. So in the E mode, you are forced to use this last binding, which is too much complex. So I skipped it in the slide. Okay. So let's see what are the free binding and the structured binding. In the free binding, as the word says, we have no a priori prescription about which data points can be connected together. So we can connect almost every data point. Okay, that's why it's free. And we realize the application by defining a kind of multicast delivery group. So we say this data point on this device belongs to the multicast group 001. All the devices having a data point connected to the multicast group 001 are binding together. So if I send a one command or a one message on the multicast group 001, all the devices receive it and act accordingly. So if I have a switch and I want to connect this switch to 3 different lamp actuators, I just put on all the data points of these devices the same group address, for example 001. In that case, when I push the switch writes a 1 on the group address, on the multicast address. All the devices are listening for this new data point value and take the action. And so we have realized the scenario, for example, switch all on, by just binding the data points together. Okay. This is free binding. This can only be realized using the rest mode configuration, so using ETS, where for each device we can get the data point and bind the data point to a group address, basically. On the structured binding, everything works almost like in the free binding, but the difference is that we can only link together specific data points. So, I I can link a switch data point with the meter data point, for example. Because there are patterns defined by the standard that say that the switch data point can only be connected to these other kinds of data points. Okay? And that's the difference between structured and free. Free, I can connect every data point to every other. In the structured, only subsets of them can be connected together. The others might be free in the structured binding. And that's why the structured binding can also be used for the E mode. Okay? Because in the E mode, the address is defined by using the push buttons or the connectors on the devices. Okay? And that's the second difference. Target binding is much more complex, so let's avoid it. So this is an example of binding. This is not a dummy example. This is the configuration of the KNX case we have in the lab, okay, with the group addresses. So all these numbers are not just put there, for example, but they are actual addresses on the case, okay. And you can see that the address format is number slash number slash number, and this is called the group address, which is the multicast delivery address joining data points together. While every device has also an individual address, which is denoted by using a point instead of a slash. Okay? And that is specific for the single device. If we want to bind the button with the plug, what we need to do is to assign a multicast address to the switch object of this device. For example, we assign to the switch object of this switch here the address 260. Then we assign the same address to the switch data point. In this case, they have the same name of the plug. And what we have done is to bind them. So if I push on 1 here, I will write 1 on the multicast group, and the plug actuator will be listening for this one and switching the relay to on. Okay, so this is just really simple if you have the software, at least. And you can bind all the devices by just binding the addresses. So if you see the picture, you have other binded addresses, like this is 242, which is for this. This is 243, which is for this one, and so on. But you can also have some unbinded addresses. For example, in this configuration, we wanted to export some notification outside. For example, we wanted to detect the button pressure. How can we detect the button pressure? We need to force the binding, because the binding only connects data points. What can we do to export a notification? We can bind this device to another multicast group, which is not existing on the network. So what happens is that the message travels on the network and passes through the gateways. If we are connecting to the gateway, then we can listen to this multicast group. We can mimic in some way a data point and get the information. And that's why you see here those addresses written in blue. All of them are open bindings, some bindings without the corresponding data point on the other side, that we use for listening information on the devices. In this case, for example, we can deduce that we can listen for button pressure. But this can only be done if we configure a proper binding on the device. Okay. Okay, let's see what is the network technology supported by KNX. Twisted pair. It is done by using just a twisted pair cable. It uses a very low voltage transmission, so there is no risk for people. They work on 29 volts, basically. The communication is asynchronous, character-oriented, and of duplex. So I can transmit, then listen, transmit, listen. Okay, but not transmit and listen at the same time. The data rate is 9,600 bits per second. Not so much, but not so slow. And The communication network uses a CSMA-CA communication, which means collision sensing. I don't remember. So, concurrent access, collision sensing multiple access with collision avoidance. That means everyone accesses to the bus, but before they start transmitting, but if someone else is transmitting, then there is a change on the bus level, basically, and this change is detected, and the devices stop transmission and try to retransmit after some time. Okay, so one single bus. This is the same access method used on the Ethernet networks. Okay. In this twisted pair configuration, all the topologies can be used. So you can use a star topology, a bus topology, a tree topology. Okay, no problem. Okay, this is a twisted pair. For the powered line, the communication happens on the main power supply network. They use a split frequency shift keying modulation. Okay, so it changes because it changes the mean transmission. The transmission is always asynchronous and not duplex, so similar. And they have a central frequency of 110 kilohertz, so much higher than the 50 hertz or 60 hertz of the main power line. But the transmission rate is very low with respect to the bus. Okay, and this is also using the same access type of the twisted pair without collision avoidance, and this is compliant to this standard. Okay, on RF they are transmitting data on wirelessly on the 8 and 68 frequency range, which is not too high for interfering with Wi-Fi connection, not too low for interfering with the typical radio connections, which are from 433 and going below. They use FSK modulation with duty cycle 1% at maximum. They use the Manchester data encoding, in which every bit is encoded with 1 level and 0 level, and what changes is which of the two comes first. Okay. So 1 0 means 1, 0 1 means 0. And this allows for tackling the noise on the transmission, basically. And the transmission rate is given by a different unit of measure, which is strange, which is named chips per second. And chips per second is the number of switches on the transmission. So one symbol in a Manchester code is 2 chips. Okay, so this is really slow. But again, we have not too much data to transfer. We have just to transfer 1 bit, basically, if we want to switch on or off. Okay. And lastly, there is the communication network that we like very much if we want to integrate everything, which is communication based on Ethernet, on IP connections. It is called the KNX-NET IP. This is the latest one. There was a former protocol which was named AEB-NET IP. We have the standard for this. There is an open library for speaking this kind of on this kind of networks, and this is mainly designed for tunneling frames between different sections of the plant. So if I have a building here and another building out there, then transmitting data over the bus is not efficient because I have distance limits, speed limits, noise limits. So the idea is to take the frames from the local bus, tunnel them into an IP packet, and then deliver the IP packet using UDP. Okay, so there's a UDP connection between different buildings, or between different parts of the building, or between the automation system and a PC. Okay, and I don't want to go as deep as the the frame format, but this is an example of frame format for the network. Something really, really similar to the network protocols that we know. So we have some control fields, some source address, destination address, type of address, some data, frame check. Okay, so this is really a network protocol, not just transmission of numbers. And the network topology is much more complex also with respect to MyOpen. It is divided basically in two main objects. One is called line. A line is a set of up to 256 devices. They are connected in a topology which varies depending on the network technology, but they form a single line. And a single line is identified by an individual address having the first two numbers equal. So you see here, for example, 1, 1, and then changes. 1, 1 means line 1, or basically means area 1, line 1. Okay? While the last number, which is the third, because they are always three numbers, can range from 0 to 255. Okay? So 256 devices per line. Then we can have 16 lines that form one area. Okay, so the second number can range from 1 to 15, from 0 to 15, sorry. So 255 devices per line, per 16 lines. And 16 lines form one area, and we can have 16 areas. So the network basically can include 65,536 devices. Many devices with respect to my home system, where they were just 255 per who function. Okay? And this can be extended because we can bridge areas using tunnels over IP. Okay? So this is the general organization of a KNX network. Okay. We have almost all the detail we need to write another page of idiosyncrasies and peculiarities of the network. So, first difference, here we have an implicit state notion. We don't have state messages. Okay? We can have state messages if we properly configure the binding. Not only, depending on the data points present on the devices, we can query the state or not. For example, the switch data point can be queried, so we can query if an actuator is on or off. But other data points, like the one for push buttons, cannot be queried. So I cannot query the state of a push button. Okay? So this is quite different from the MyOpen system where I can query everything. State events can be generated. They are not native. We need to carefully configure the devices. And we can do that only in S mode. And that's why I was saying we always use ETS. Because we can have state changes only if we use the software for configuring the devices and handling the excess binding needed for a state change. And we need to be really careful in the configuration because we need to define proper group addresses, one per each device we want to listen. Okay? So we are wasting group addresses for listening to state changes. And we need to configure the gateways for passing through unbounded groups, because the default gateway behavior is to filter. So if I have a group address, the group address is limited to the area or to the line. Okay? But if I want to listen to these messages, for example, by connecting with a PC, I need to instruct the gateway to pass through these messages. And these are the disadvantages. The advantages are that in this way, all devices can publish state changes. So we can also detect the state change of a button if we configure it correctly. And in addition, all devices usually have a specific data point, which is called in operation, that tell us if the device is working or not. So we have also some diagnostic events running on the network. In the KNX net IP connection, which is the one that we want to use if we want to interface the system with the computer, we have two connections mode. Actually, there are maybe three, but two are the main. But we use only one, which is the tunnel mode. Why? Because the tunnel mode is the one which allows tunneling frames from one network, from one area to the other. And that's the only communication mode where the frames running in a specific network area are passing through the gateway for going towards another area. And we need to work in that mode because otherwise we cannot listen on the network. Okay. But the good news is that there is a specific connection mode that can be opened at the same time of a tunneling mode, which allows for partial device discovery. I'm saying partial because we can discover what are the devices on the network, but we don't know where they are and to what abstract device they correspond, because we discovered the data points. So I discover something that has a switch data point, a meter data point, and so on. But I don't know if that is a meter, an actuator, a lamp switch, I don't know. Okay? So that's why I was saying partial. And this is a common problem for other protocols. For example, in Z-Wave, we have pretty similar, the similar problem, where we have classes of devices, but we don't know which devices actually. If we are trying to connect to the network using the old protocol, which is the one used by the dog drivers, the older dog drivers, we need an additional requirements to be part of this multicast group, because the tunneling information is sent to a multicast address. Okay, so if you are not joining this multicast address, you cannot listen to the network messages. So, even just on the state part, we have some discrepancies between this technology and the former one, the BTC one. Plus, we have differences on the kind of connections. Okay. Last one. I know this is really annoying, but just to get the complexity. This is Modbus. I choose to show Modbus because it's actually pretty similar to many other protocols like Echelon, for example. Okay. And it has a completely different approach to the same problem. It derives from a quite old standard in the industrial side. It starts with the OSI layer representations, and it locates at the level 7, which is application, the top level. It is designed for working on different bus technologies, and it's old. It was firstly designed in 1979. It's really old. And the interaction between devices reflects this old design. In fact, it is based on master-slave connections. Okay? Where the information required for activating or deactivating devices is based on function codes. These function codes are part of the messages exchanged by the devices, and these messages are called the PDUs, protocol data units. And this is the general architecture. You see, much simpler than the Connex one. There are connections of using different technologies. For example, this one is using RS485 serial. This is a serial connection. This is another kind of serial connection, RS232. These are quite old, and they were the first used by the protocol. Then there is a Modbus connection on MBus, okay, and here, for example, a Modbus connection on TCP/IP. So different communication means running the same protocol. And this can be done because the protocol is a level 7 protocol. Okay? So it's independent from the network layer. And you can see here the examples always involve a PLC, an I/O, and HMI. These are older terminology. PLC is programmable logic controller, which is a control system for the industry, basically, for automating processes. I/O are what they mean, so input and output devices. HMI are human-machine interfaces, so displays, keyboards, and whatever. Okay. So the idea is that all the devices are connected and can exchange messages using the Modbus protocol. The Modbus protocol is based on a protocol message. It's a level 7 message. It is structured like every message on a network, so it has a preamble and a concluding element for error checking. And then there's a payload, and this payload is basically divided in a function code and a data code. Okay. Function code identifies what the data is meant for, and the data is the data, and it changes on the application. Okay, this is really abstract, nothing really new. Okay, let's dive a little bit deeper in the protocol. The function code identifies which action to perform, uses 1 byte, so we have 256 different function codes, but only some of them can be used. In particular, those from 128 and 255 are reserved and used for exceptions, for errors. So we have just 127 function code, different function code. 127 because the function code 0 is not valid. Okay? If we need some more specification on the actions, because we have just 127 different actions, quite a bit, but maybe we need to specify better a single function, then there are available some sub-function codes. So inside the function I have some function, something similar to the what plus parameters in the MyOpen system. And this is just a table for scaring us. So the function codes and the corresponding operations. So for example, physical address, so the function code 01 means read coil. A coil is what you need to operate a contact on a relay. So it's the electromagnetic part which attracts or not the relay contact. So if I want to read the coil, I want to read the state of the relay, 1 or 0, closed or open. And if I want to write the coil, I want to change the state. Okay? So something is starting to emerging. Here we read and write values instead of sending commands or receiving commands. And then there are many others, more complex. So for example, if I want to get some data on the value of the current voltage on the line, I need to read some 8-bit or 16-bit data, pure data that I need to interpret in some way. And we have this function code. So for example, read all the registers, read multiple registers, and so on. So another important thing in the Modbus is that we have this concept of register. A register is just a place in memory where there is a value, and this value might correspond to a state of a device or to a value measured or extracted in some way by the device from the real world. And on the other side, if we want to change something in the real world, we need to change those values to write in the registers. So this is a really quick example of protocol communication. So usually it's a client-server, master-slave communication. The client starts by requesting some operation, by sending a function code and data request. For example, function code 1, 2. Let's say I want to write coil, and data is 1. I want to switch on something. Then the server, which is the device in this case, performs the action if it can, and sends back an acknowledge in this case. Okay, the operation went good. I switched on the call. And the client receives the request. So it's a client-server approach. And the same happens if we have any error. So if I send the wrong function code to the wrong device, I get back an exception function code. Okay. Everything works on the basis of a data model, which is based on 4 primary tables. This is much more complex than KNX in some way. There are some distinctions between inputs and outputs, between registers that contain bits and words, and registers that just contain calls. But all these distinctions do not imply anything on the application side. So every vendor may use these registers to do something different. So if I want to expose a contact, open and close, I can expose it like a coil, or I can expose it using a particular register in which I need to write some value. The tables can overlay one the other. So I can have a write coil that actually correspond to a physical memory part, which is overlapping the physical memory part using by a word register. So if I write the word or if I write the coil, I may have the same result because they are overlapping. They just offer a different way of accessing to the same data. And since we have sometimes data which are larger than 8 bits or 16 bits, the items can span multiple registers. So if I have a 64-bit item, I span 2 registers. Okay. So this is an example. The 4 tables are this one. Discrete inputs, which usually take a single bit information. They are read-only and then provide data extracted from an I/O system. So digital I/O basically. Coils, they are also single bit, but they can be read and write. And the data type can be changed by the application, so I can write and read it. And then there are words, input register and holding register. The difference is that the input register comes from an input-output system, while the holding register usually is written by an application. Okay. And they can be overlapping. So for example, in this case, this device, this is the memory of a Modbus device, maps the discrete inputs, the coils, the register, and the holding register in different memory zones. So when a request comes, depending on the function code, on the type, it will be setting values in different parts of the memory. And this will correspond to some action on the device. But they can also be overlapping. So a single memory part, a memory block, where all the tables are overlapping each other. So for example, coils are just pointing to this bit in this 8-bit memory. The discrete input, for example, just to this bit, and the others to the whole block. Okay, and this depends on the vendor. Really complex. So basically, if we want to read and write data on a Modbus system, we need to read and write registers to make it short, and we need some kind of mapping between the functions and the registers. And that's why every Modbus device has a leaflet saying at the address 1001 you get this data, at the address 1002 you get this data, and it takes 2 words. So you need to read also the register 1002 and so on. Okay, and this is how the communication works. So when a device receives a command, first it checks the function code. If it's wrong, it sends the exception function code number 1. After it validates the register address, Okay, so the register actually exists, yes or no? No, another exception code, otherwise go further. Then validate the kind of data. So if I want to write a word on a single bit register, I cannot. Another exception will be thrown. And finally, we'll execute the function if everything goes well. If the function generates an error, there will be an exception back. If the function is executed correctly, then a response will be sent back. Okay? So it's really controlled in all the steps. Okay. This was for the protocol. Let's relax ourselves by looking at the network technology, which is much easier. Many network technologies, the former is the easiest one, other, so everything. But the main ones are based on either Ethernet, serial connection, or some Modbus specific connection. So the idea is that we can either work on serial connection, RS232 or RS485, and this allows for interfacing, for example, older meters and all the meters which are exposing this kind of interfaces. This is very much specific to Modbus, so it is not so diffused, basically. This is the most diffused. And we have also an Ethernet connection, which allows to span the system over big distances. So, for example, here at the Politecnico, we have some Modbus meter connected to the Ethernet. They are, for example, located, I think, almost here at the beginning of this building, and they go to the university network up to a room which is over the rectorate, so at the beginning of the building, so very far from the measure point, and that's why they have this Ethernet connection for enlarging distances that can be connected together. It is based differently from Connex. This is based on a TCP/IP layer using a connection-oriented connection. So I send a message, and if the message gets lost on the network, it will be retransmitted on the network. Few things, just that Modbus Plus, it's a token ring network, some kind of really old network technology, which has the feature of being really high speed. So it's used basically locally for implementing real-time controls. Okay, so returning back to our problems. What are the problems to integrate this technology? States. Here we have an explicit state notion, but we can only query the state. We don't have events. We have just register to read and write. So, no asynchronous working, no event-based. If we are lucky, we can just poll the information. There is no command option, notion. We are not sending command. We are just writing registers. So we need to find a mapping between a value on the register and a command. For example, if I want to switch on a lamp, I need to write 1 in a specific register. This is a client-server approach, so I'm not listening. I'm always requesting something and waiting for responses. There is no device notion. I don't need that the register is a device. If I have a set of devices connected to a Modbus gateway, and this is the case, for example, for the Modbus case we have 3 meters connected to one Modbus gateway. They are all exposing their registers through the gateway, but if we look at them from outside, we don't know which register corresponds to which device. So we have no notion of the device. We have just notion of the register. The only thing that we can use is the slave ID. So if we have a gateway, it acts as a master towards its slaves, and every device is a different slave. So we will have a slave ID, which is the only information we can leverage for understanding to which device we are speaking. But the registers are all exposed by the same device, which is the gateway. So it is masking the devices lying behind. And there is no device discovery. I cannot discover what are the devices on the network. I need to know what are the registers. And the registers change from device to device. In fact, for every device I get a leaflet with register address function. Okay, so I cannot assume that register 1000 is always a switch on, the coil switch on the light control, for example, because it changes. Perhaps in a meter it means the general voltage or the general failure information. Okay, so after this big, long, and annoying description of networks, what do we need to care if we need to design something for Docker, some driver for Docker? So the idea is that we have all these different requirements, all these different technologies, and we want to gather all together them and to represent them in a uniform way. Let's go back a little bit, or let's go further, since we still haven't speak about dog and gone. What we want to do is to represent everything in a uniform way. And this uniform way is defined by an ontology. This ontology basically describes devices using a state and functionality based representation. So a device is characterized by these functionalities, which are the commands it can receive, the notification it can send back, and by the possible states it can assume. So a lamp, it's a lamp that can receive the on and off command, that notifies nothing apart the state change, okay, and that has two possible states, on and off. And we need to conciliate, to find a way for extracting this information from the network level information. The second assumption that we have in DOG is event-based interaction. No matter which is the network, we want to work event-based. So we want to have events coming from the real world, and we want to generate events toward the real world. And this, we know, doesn't correspond to the reality. If we are interfacing a Modbus system, we cannot do that. So we need to find a way for changing the way devices interact. And all the networks should be isolated, abstracted, forced to work in the same way, so that up of the representation, everything is the same. A lamp is always a lamp, independently from the network. So what we need to do practically, and this is a kind of first taste of what we will be doing in the next presentation, which will be about DOG, we need to write a network driver for each technology we want to interface. And this general network driver is organized into three modules. The first, which is the network driver, which is mandatory, so we need to have a network driver, which is charged to connect to the network, handle the event delivery. That means if the network is not event-based, convert the network to an event-based network, for example by polling. And it needs to handle connection losses, and all the other problems that you can have with a real network. Okay? And this is the first. This should always be there. This is independent from the configuration. If we don't have devices in the home using that technology, but we have that technology supported in DOG, then we need to have a network driver. Then there is a gateway driver. This is optional because we may have big installations where we have different aisles of technologies. Every aisle speaks with the central system using a gateway. Then we will have just one network driver, because it is the module that knows how to communicate with that kind of network, but many gateways. Okay, so we need a gateway driver that basically knows to which real gateway deliver the information, encoded by the network driver. Okay, and then usually we have more than one device driver. I'm saying more than one if we want to support the network. Otherwise, we can interact. So, if I want to have a lamp supported in Modbus, KNX, and MyOpen, I need a lamp driver for the Modbus technology, which interacts possibly with the gateway driver if there are more than one gateway on the network, and surely with the network driver for sending the data on the real network. And the same happens for the KNX and for the MyOpen system. Okay? So 3 lamp drivers if I want to support 3 technologies. Really straightforward. Okay, now how can we address the problems? So I try to shorten here what are the problems and identify the conversions. So we have the Open WebNet network. We know that it works based on the who, what, and where tags. And we know that we can have event-based interaction by using a monitoring session. On the other side, in Docker, we represent a device by means of a URI, by means of its commands and states, and by means of its notification, which are basically the events. Okay. So the URI corresponds to the where tag. So we need the mapping between the URI and the where tag, and this is done in the network driver. Then the commands correspond to the couples who and what. So on for a lamp is 11. For a webcam is 70. Always a couple, and we need the mapping for this. And notifications are the same, but in the opposite direction. While command is going from dog to the network, the notification is coming back from the network through the monitoring session. States, unfortunately, they are using the same couple, what and where, and they are also coming from the network. But we can query them, so they are kind of notification and command at the same time. So we can query the state, or we can get the state as a notification. Okay, and if we want to work on event-based interaction, we need to open a monitoring section. So here the mapping was really simple, actually. Apart this confluence of commands, states, and notification on couples of what and where. Okay, but this is really addressed because actually we know the commands only go from the application to the network, and notification only go from the network to the application. So we can distinguish them. And states can be commands and notification at the same time. And we got it. With KNX we can do the same thing, but this is a little bit more complex. We have the URI on the dot side, we have the individual address and the group address on the KNX side. And actually, the mapping is between one URI and one individual address plus one group address. Okay? It depends on what we are doing. Actually, the driver that we have only uses the group address, which is sufficient because we are associating a device with a binding, basically. Okay? Then the commands are represented by a couple of group address and specific data point. So if I want to send a non-command, I need to have the group address to which send in the command, and I need to know that the data point is a DPT switch, for example, which is the data point for switching things. Okay, and these are defined in the network. So if you try to open the network driver of KNX and the on-off driver, you will see at some point some indication saying DPT switch or DPT, I don't know, something else. These are the standard data points used. So the drivers are establishing this association. Notifications are exactly the same, but for getting them, we need to properly configure the devices and configure the gateway to pass through the messages. Okay? So we listen to the group address events, but we need to be able to have those events by configuring the gateway. States are a little bit more complex because they always map like the other on group address and data points, but they are not always available. Not for all devices. Some of the devices can't be queried. Okay? So if we want to know the state of a button, we cannot. Maybe we can listen to the notification. Because if we correctly set the binding on the button, an open binding, then we listen to the message sent by the button data point. So we have the state change notification for the button. And we need at the driver level to bridge, to fill the state using this state change notification. Okay? So we can still get the states for all the devices, but the complication is higher. And even this interaction can be easily obtained if we configure correctly the plant. That means that if we go and in a building with an already existing plant, might be we cannot listen to states because someone else has configured the plant, and if the electrician or the designer has configured the plant in a way different from the way we need for listening to events, we cannot. Okay. So if we are trying to bridge or to connect to an existing plant, might be we need to modify the plant configuration if we want to listen to everything. Or otherwise we don't have notification. Modbus, much more complex. So now the URI is the set of register, address, and slave ID. The slave ID identifies the device and the register the function. So a lamp is, for example, the register 1000 on the slave ID 3. The slave ID 3 actually is the ID of the slave of a light actuator with 3 different channels, and the first channel that corresponds to the first lamp has the 1000 register. Okay? So the couple of the two correspond to our URI. Comments are easier. If I want to comment something on the Modbus network, I need to write. Okay. So one-to-one mapping. And if I want to get the state, I need to read. Notifications are a little bit more complex because we cannot have events from the network, as the network is based on a client-server interaction. So what we need to do is to poll the network. So constantly reading and pushing back notification. Reading and pushing back notifications. In doing this, we will have, of course, some delays because it depends on the polling cycle. But all of these complex things should be done and should be confined to the network driver, so that upwards everything is the same. Last consideration, what about the other technologies? Some that we know, some that we don't know. Almost the same thing. So we need to identify the idiosyncrasies and we need to mask them. In that way we have some similar idiosyncrasies to Modbus and some to KNX basically. So in that way we cannot have events. We need to poll the devices, especially because battery-powered devices are not always available. So they come alive, you can query them, then they switch off for saving batteries, and then you cannot query them. So you have polling, but the polling depends on the state of the device. So might be you have 3 cycles of polling failing, 1 getting the data, and so on. It supports device discovery, so it requires some facility for creating new devices in DOG. So the network driver must be able to instantiate new devices, and especially to associate the correct type of the device to the real device description that we get from the network. That in turn is pretty similar to Modbus. So we don't know actually what is the device, we only know what are the classes, what are the kind of registers, let's say. that the device has. So if we have a tripole sensor, it will expose a presence class, a lighting class, a temperature class. And might be we don't have a device representation bridging all these three capabilities. In that case, we need to decide what to do. Maybe just representing a subset, maybe trying to invent a new device at runtime, and so on. Okay, but this poses a problem on the abstraction. And we have the same implementation constraints of the Modbus, because we need the polling, we need one driver, one gateway driver, more than one device driver. Echelon is really easy because it's a different kind of Modbus. It works exactly the same. So you read and write registers. So when you write a driver for Modbus, then you can convert it to Echelon by just changing a few lines, actually. So it's really easy. And the others, it depends on the documentation. So our first problem is documenting, so understanding what is the protocol, what are the problems. More or less now we know what are the things we need to take care of, so states notification basically, how they can be represented, how can we send commands, and then we can start developing drivers, so integration in those. Is finished? Okay. Sorry. Okay. So really long, really annoying might be. Okay.
I have a question just to clarify.
Yeah.
So if we take the example of Z-Wave, the Z-Wave network driver we had, for instance, the Z-Wave controller previously that we use is the gateway driver.
No, it's the physical gateway.
Okay,
Then you need a driver for speaking with that gateway, which is composed by two modules. One is the network driver that knows the protocol and opens the connection, and the other is the gateway driver, which allows you to have more than one pen plugged. Okay? That's the difference, basically.
Yeah, I was clear.
Okay. Other questions? Okay. So either it was clear or too long.
No,
Okay. Perfect. Okay, I will put the presentation on the web so that everyone can.